Okay, one important concept remains before we close out this chapter. It is called potential vorticity. Tends to be conserved under certain conditions which are valid in the interior ocean, and turns out to be a very robust concept and constraint also in the atmospheric circulation, and conservation statements are always important. We've been looking at mass, energy, and have done many calculations with those. This is the concept of vorticity you probably know. So the potential vorticity has a specific connotation where, again, potential means it is there but not always manifest, and there are ways in which it gets manifest under certain conditions. So let's start with the more general equations of motion that we derived in the earlier part of this chapter. F equal ma statement, where we had the momentum equation in the zonal direction, meridional direction, and the vertical, which we simplified to hydrostatic balance, and we had F, the forcing, on this side as the pressure gradient, either bottom bottom stress forcing or surface wind stress forcing, and the Coriolis effect. And of course we derived a simpler version of this for shallow water model. What we are going to do for potential vorticity is to look at a more general realistic structure of the ocean. We have again the ocean bottom and the ocean surface, neither of which are flat, and in between we have, away from the surface and away from the bottom, typically have a very strongly stratified ocean where temperature and salinity together determine the density stratification of the ocean, and you have constant density layers here varying, let's say, between rho and rho plus delta rho, with varying thickness h, which have the ability to change or have density changes created by what are called diapicnal fluxes. So we talked about isothermals, and you also have isohalines where salinity remains constant. These are called isopicnals, and you can imagine that crossing the density lines and creating new densities is energetically much more difficult than flowing along constant density lines, because the reason why strong stratification is maintained at any time is that such mass transformations are not very routine, they're not very fast. You need special forces to be able to do that. In this case we are looking at the vertical cross section, of course, showing a part of the discontinuously stratified ocean. Just means that there are density layers varying between two densities, rho and rho plus delta rho. Providing the stratification is stable, the water of the lower layers are denser than the water of the upper layers. Static stability requires that density increase continuously, so in this case delta rho has to be greater than 0. Eddy fluctuations W prime of the vertical velocity W occur and yield mean eddy mass fluxes plus minus W prime rho prime. So the eddy covariance that we talked about before, so that amounts to plus minus W prime delta rho between layers. This is a very general description, but just keep that in mind and bring back your memory about the shallow water solutions we derived by looking at vertical cross section showing a part of the ocean. So we had average thickness h here from the surface elevation to the bottom, and that had surface elevation variations in x, y, and time. Bottom depth, of course, remains constant, ocean bottom, so the average depth h over time was basically going to give us z at any depth as minus h plus eta b. So depending on whether eta b is positive or negative, you had h increasing or decreasing, and local layer thickness h was h plus eta minus eta b. I'm not going to go through this again, but you know what we mean by here. So in that case, we had defined h as h plus eta minus eta b, where h as well as eta b are time independent. Obviously, average depth by definition is something that didn't vary in time, but local depths varied based on sea surface elevation and eta b locally, and the mass continuity in this case transformed into thickness layer change, so del H del T, plus the flux in the zonal and meridional directions duh dx plus dvh dy equal to 0, because we didn't have any mass source or sink. So we take this form and write for this case a similar equation where now we have to allow rho to be non-constant to start the derivation. So d rho h dt plus del del x u rho h plus del del y v rho h equal to q, where q is of course this diapicnal flux where mass density changes are being introduced by the eddy fluxes, or mass is being introduced by eddy fluxes. Okay, so eddy mass flux in this case is of course plus minus w prime rho prime bar, as we have seen before. So keeping in mind again our general material derivative equation for any quantity A, where the Lagrangian material total derivative dA dt is partial A partial t plus the flux terms u dA dx v dA dy plus w dA dz, and that gives us the layer thickness equation in this case as dH dt plus h times du dx plus dv dy equal to q over rho. Again, we are zooming into isopycnal layer, and assuming we are moving along these layers and rho is constant within a small range, so we're going to take rho out and write this equation as rho here, q over rho. And of course we're going to look for special solutions where q then becomes 0. So this is a good time to define vorticity. So this is vorticity zeta equals to curl of the velocity vector curl cross or grad cross u dot z unit vector. So we are looking for vorticity in the local horizontal plane. Remember, we are still on a sphere, but we are locally going either into f plane or a beta plane, and we are going to derive local vorticity around the vertical axis. So if you curl your fingers with u and v gradients, dv dx minus du dy has vorticity in the z direction, so the cross product is dotted with the local vertical z hat. So this is called a relative vorticity. Why? Because we are on a rotating framework. The planet itself is rotating, so anybody who is on the planet has a vorticity that is induced by the planetary rotation itself. So any vorticity you have on top of that is called relative vorticity. So obviously there is a concept of absolute vorticity, which we'll come to in a minute. Here is a way to think about it. Vortex in the form of a solid disk rotating with angular velocity omega about an earth fixed z axis. So z is coming out of here. You can think of this as longitude and latitude. The velocity the velocity of the points of the vortex at a distance r from the center is omega times r. You can easily imagine that. So here you have v perpendicular to x, so v is omega x in this case, but at any location the tangential velocity is omega r, right? Here you are perpendicular to y, so you become zonal velocity equal to minus omega y. It's in the negative y direction. So our verticity then, dv dx minus du dy, becomes 2 omega. So du dy is omega, dv dx is minus omega, so you have so minus plus, so we have 2 omega. So relative verticity here becomes 2 omega. So if planet is rotating at omega, which would typically represented with capital Omega, then the local relative verticity is 2 omega, which actually that's not relative verticity, that is what every particle on the disk has, but we are going to do this locally. So instead of omega we use f, which we had done before as 2 omega sine phi, if you remember the projection. So keeping all that in mind, we come back to the special shallow water equations we had derived in the case of the shallow water equations we have derived. I don't know why I'm fumbling this with this situation, where we wrote the equations again: du dt u du dx plus v du dy equal to minus del eta del x plus f v, and dv dt plus u dv dx plus v dv dy equal to minus g del eta del y minus f u. And we had real, remember we created real forcing and apparent forcing. So the real forcings were pressure gradient and the forcing at the surface, and real forcing in the y direction was pressure gradient and the meridional wind stress forcing, and in the vertical we had hydrostatic balance. Okay, so this of course could be bottom forcing as well, depending on which situation you are dealing with. So we are going to go back to the equations of motion that we looked at here and do d dy minus d dx as we did before to get our verticity equation. So here we're going to take d dy of 613a and d dx of 613b. So just adjusting the values, you had du dt, so we're going to write it as d dt du dy plus du dy du dx plus u d squared u dx dy, you know, law of partial differentiation, plus dv dy du dy plus v d squared u dy squared equal to the forcings dax dy plus the Coriolis term where you have df dy plus times v plus f times dv dy on the right hand side. Similarly, for the meridional direction you have these terms of differentiating the equation dv dt plus u dv dy plus v u dv v dv dy and creating a parallel equation in the y direction. Of course, you can take the difference and write this as d dt of dv dx minus du dy plus u du dx of dv dx minus du dy, you know where this is going, plus v d dy of dv dx minus du dy. So in each case we have zeta, the verticity, so obviously we are creating a verticity conservation equation, plus du dx times dv dx minus du dy plus dv dy minus times dv dx minus du dy should be equal to dy dx minus dax dy minus df dx u minus df dy v, and these terms minus f du dx minus f dv dy. Okay, so that's just a simple operation, nothing to panic about. Just look at them and make sure you understood all the steps. So just substitute this expression with zeta, the relative verticity, and voila, we have d zeta dt plus u d zeta dx plus v d zeta dy plus du dx plus du dy. You will already recognize this as convergence divergence in the horizontal, plus times zeta equal to dy dx minus dx dy minus df dt, which is of course 0, minus u f dx, which is also 0, doesn't vary in the x, minus v df dy, which is beta, minus f du dx plus dv dy, which is again the horizontal divergence convergence term. You can simplify this now and write as the Lagrangian derivative by combining the appropriate advection terms. So d dt of zeta plus f equal to minus zeta plus f, we're just clubbing terms together, times du dx plus dv dy. So we went from relative verticity zeta to zeta plus f, where f is the planetary verticity. So it is the verticity we all acquire just because we are on the planet, so it is not felt because we are moving with the accelerated framework. But if you use the unaccelerated framework, then that's the total or absolute verticity zeta plus f, and this is the convergence term. So each water parcel, let's say, is carrying total verticity. When water masses converge or diverge, you're going to change the verticity, and that's this term. And then there is a production term that is related to the forcing ay and ax. So day dx minus dx dy is the production term. So obviously we're going to go back to the Stommel wind forcing problem, where wind stress had a curl. Remember that you had trade winds in the low latitudes, westerlies in the mid latitudes or subtropics, and we used our right hand rule to curl our fingers with the trade winds in the low latitudes, westerlies in the subtropics, and we got verticity pointing down. So wind is producing a negative verticity in that case. And we also had the western boundary, where flow was against the boundary, and the boundary friction was able to produce a curl as well. So obviously we have derived the verticity conservation equation to go back to the wind-driven circulation to put it in the full framework and give it a more holistic picture of exactly what's happening in the wind-driven circulation, which we had left explained in terms of western boundary intensification, but we hadn't explained why the western boundary is in the west, even though we said beta gave us western boundary intensification. We didn't say why that was not in the eastern boundary. Mathematically speaking, you could also have a boundary current in the east. So that question can be answered here. So writing our real forcings ax, ay, and az again as minus 1 over rho dp dx plus 1 over rho d tau x z d tau x z dz. Ay is minus 1 over rho del p del y plus 1 over rho delta y z del z, and az is the hydrostatic balance. So we can then write day dx minus dax dy as, these pressure gradient terms get cancelled out. So you get 1 over rho del squared tau yz del x del z minus 1 over rho del squared tau xz del y del z. Okay, so in this case the pressure terms disappeared, and that makes this fluid the production by real forces is independent of the pressure gradient forces. Such a fluid is called barotropic. We used this term before. All others are baroclinic. So barotropic is where pressure surfaces and density surfaces are parallel to each other, and the cross product of grad p cross grad rho is 0, whereas in the baroclinic fluid the pressure surfaces and density surfaces can intersect. In a barotropic fluid, the change of the absolute verticity results solely from the circulation convergence and verticity production due to friction. Okay, so those are the equations we are looking at still. This is the continuity equation where if there is no mass source, this goes to 0, and that's our total verticity equation which we derived for this fluid. Maybe I will stop here and continue this discussion because this is already 20 minutes, but make sure you go through the equations and understand the derivation. It's fairly straightforward, but the concept is very, very important, and we'll explain the physics of it in the next podcast.